Back. This time we're going to talk about conditional probability. I'm going to return to the Lego example that I did with the kids in a different video. So this is a count and a Venn diagram of various Legos. There are 20 Legos. The large ones are denoted here, and the small ones are denoted here, and they have 5 different colors. So in the situation where we had these Legos, we could assess various probabilities of having different features, different colors or sizes. And I want to repeat a little bit of that to remind you how we're counting in order to calculate these probabilities. So quickly, let's calculate the probability that a random Lego drawn from this pile will end up red. So this will simply be the probability of getting a red Lego. And that will be 8 over 20. It's 8 because there are 8 red Legos represented here, and there are 20 Legos altogether. So 8 over 20, and that's 0.4 or 40%. So a plurality of these Legos are red. There are more reds than others, and so we have a 40% chance of drawing a red Lego. The probability of getting a large Lego, some of them were large and some of them were small, is going to be, we count up these. So there are 10 large altogether here, and there are 20 Legos, and so that's 0.5 or 1/2 or 50%. So it's a toss up. So probability of getting a large Lego is 50%. Now, so in fact, being large and being red are independent in this case because among all the Legos, exactly half are large. And among the red Legos, exactly half are large. But that's not true for other colors. For example, among the blue Legos, we have 2 large and 1 small. And that means that if we know that a Lego is blue, then we know something about its size, not something certain. We don't know for sure that it's large or small, but we do know something about the probability of it being large or small. And that probability of being large or small changes with the knowledge that the Lego is blue. So even though blue and large are very different concepts, if this is the arrangement of Legos that we have, and if we have chosen one and we know for some reason that it's blue, then we do get updated information about how likely it is that that Lego would be large. And so this is called a conditional probability. It's a probability which is under a certain condition. That is, we have some partial knowledge about the state of affairs, and then in the presence of that partial knowledge, we try to assess a probability of something else. So the way we write this is we write the same, probability of an event, but we put the condition after a vertical bar. So the probability of being large, then we put a vertical bar, and we write blue here. So what this means here, this is the condition that we know, and this is the thing that we're trying to assess the probability of. And let me write out this in words. This is the probability that a random blue Lego is large. That is, it's the probability of the large event if we know that the blue event has already occurred. So if we know that the blue event has already occurred, there are only 3 blue Legos here. And so and then 2 of them are large. So the number of successes here is actually 2, and the number overall is only 3, not 20, as it has been for all of the other examples. And so we get 0.667 or 66.7%. I'm rounding, of course. That's, it's 2/3 if you want the accurate number. So this is a conditional probability, and we can calculate it based on partial knowledge of one feature. What is the probability of another feature? Let's do another one. Let's do the opposite one, actually. Let's do the probability that a Lego is blue, given that that Lego is large. So you might imagine, to make sense of this, imagine that the Legos are in a bag and they're drawn randomly from the bag. But imagine that when doing it physically, you reach in without looking and you feel with your hand along the Legos in the bag, and you can tell, right? You can feel, you can't tell the color unless you have really sensitive hands. You can't tell the color, but you can tell the size. And so even as you're feeling out without looking, you can pick one which is large. And so if you intentionally do that, what is the probability that it will be blue? That's what this is asking. Given that it's large, how likely is it that that Lego will be blue? Now, this will not be 2/3. Given that it's large means the only Legos that we actually have to be concerned about are these large ones up here, and there are 10 of them. 2 of them are blue, so we have 2 successes and 10 options, which is 0.2 or 20%. So there's a 20% chance of being blue, given that the Lego is large, which is, an important caveat which changes the probability. This is not the same probability as the probability of getting a blue Lego if we're drawing at random. The probability of getting a blue Lego if we're drawing at random, just to illustrate that, is 3 out of 20, or 0.15, which is 15%. So if we draw truly randomly, we have a 15% probability of getting blue. If we draw only among the large intentionally, then we have a 20% chance of getting a blue Lego. And so, if you, for some reason, really want that outcome, then cheating in that way might be a strategic way to get that outcome. Who knows whether it would really be cheating, or maybe that's following the rules. I don't know. So this is what conditional probability means. It means you assume one thing, you get a condition that you somehow already know to be true, and then in the presence of that, you assess the probability of other conditions or outcomes. Let's do one more, and then we're going to need a more sophisticated formula for this other than our basic counting formula. So let's do one more example of this before we move on to a more sophisticated formula. I want to assess the probability that a Lego is red, given that it is small. So this will be the probability of red under the assumption that the Lego is small. So for this calculation, we only need to consider the small Legos because we're given that it's small. So how many of them are there? There are 10, and then 4 of them are red. And so this gives us 4 out of 10, which is 0.4 or 40%. So if you choose a small Lego, it has a 40% chance of being red. That is, the probability of being red, given that the Lego is small, is 40%. Now, I did this example in order to illustrate something here. Notice that the probability that a truly random Lego would be red is also 40%. And the reason for this is that the red is kind of evenly balanced between the large and the small. And as we talked in another video, in this situation, the red condition and the size condition are independent conditions. And this will always happen when we have independent conditions. Conditioning on small doesn't do anything to the probability of red because red and the size condition are independent variables here. And so the conditional probability under the condition of small was the same as the more absolute probability of simply being red. Now, this is all well and good if we have the exact counts in front of us, but often we don't, right? Sometimes we know that the survival rate of a certain condition is this, and that the probability of this other thing, maybe this comorbidity might be this other probability, and sometimes we have these things on the level of probabilities, but we don't have the same information on the level of raw counts from a complete data set like this. And so if what we have is probabilities, then we cannot assess conditional probabilities by simply referring to the counts involved, as I have in all of these examples. And so what I want to do next is I want to teach you a rule for establishing the conditional probability on the basis of the various probabilities that you have. So let me explain. So in general, this is a general rule for calculating conditional probability. The probability of A given B is going to be the probability, so A and B is going to be the probability that both of them happen divided by the probability of B. This is basically what I have been, you might look at this and say, isn't that just exactly what we've been doing, right? The probability of large given blue, I take the probability of being blue, 3, and the probability of being both, 2, right? And I divide them. Isn't this exactly what I've been doing? Well, not exactly, because these are supposed to be probabilities in this equation, and those were raw counts, right? The probability can't be 2, nor can it be 3. So this is actually different from what's going on here, because this is dividing the raw counts, but this is dividing the probabilities. But it is directly analogous. Basically, we're still trying to effectively count how many cases are type B, and count how many cases are A and B, because we're only thinking about B, and then we're trying to divide. So what I want to do next is I want to take this general formula for the conditional probability, which is a super important formula, and I want to apply it in these cases that we've already done and see that we get the same answers here. So in order to do that, let's squeeze it in here. So we're going to take this first example, the probability that the Lego is large, given that it is blue, and we're going to recalculate it using this formula. So the probability of large given blue is the probability of large and blue divided by the probability that it is blue. Now, what's the probability that a Lego is large and blue? Notice that both of these are just absolute compared to the whole. Large and blue, that would be, there are 2 of them out of 20. So this will be 2 out of 20. Oops, I wrote that wrong. 2 out of 20. And this is the probability of being blue. What's the probability of being blue? That's 3 out of 20. And that, of course, is the 20s cancel and we get 2/3, and that's the same thing that we had before. So you might say, why would you ever do it this way? If you have the raw counts, you would not do it this way. You would do it in the original way. But if the only information you have to work with is the probabilities, then you cannot possibly do it this way based on counting. Then you would do it this way and you would plug in the probabilities. However you knew the probabilities, however you got them, you would plug them into this formula. So let's do another one. Let's do this next one, the probability of being blue given that it is large. So the probability of being blue, given that the Lego is large, is the probability of being both, so blue and large, divided by the probability of being large. Now, what's the probability of being blue and large? We discussed it up here. It's 2 out of 20. I'm going to write that in decimal this time just to mix things up a little bit. The probability of being blue and large is 2 out of 20, or 0.1. The probability of being large is 0.5. And so the probability of being blue and large divided by the probability of being simply large is 0.1 divided by 0.5, which is 1/5, which is 0.2, which is 20%. Maybe 20%. And notice that's consistent with what we got in the previous exercise by merely counting. The point here is that you might know the probabilities, but you might not know the raw counts among some greater population. And so you might have to do the work this way. Now, if events are independent, then the probability that both of them happens is the product of the 2 probabilities. So what we'll get is the same thing will happen. So I want to point out here, I want to remind you what happened among the reds here and here. And I want to point out what happens with conditional probabilities if the events are independent. So, so let's write this here. So if A and B are independent events, then as we've seen for independent events, we have a product formula for them. So if A and B are independent, then the probability that they both happen is equal to the probability that one of them happens times the probability that the other one does. This is not true in general. I don't want you to overuse this formula here. Most of the time when talking about probabilities, the probability that 2 things happen is not the probability that both of them do. It's only when those are independent events, okay? So if we have independent events, then we have this product formula. So in this case, the conditional probability of A given B is the probability of A and B divided by the probability of B, but A and B just has a probability A times B. So that's probability A times the probability of B, I wrote it badly, times the probability of B divided by the probability of B. And here you can see the probabilities of B cancel here, and that's the probability of A. So only if the events are independent, we get some cancellation here, and a conditional probability, the probability of A given B, works out to simply be the probability of A, which is what we witnessed here and here. The probability of just being read is 40%. The probability of being read, given that the thing was small, is 40%. And the reason the conditional probability was the same as the absolute probability was because basically knowing that it was small didn't give you any extra information, because small and red are completely disconnected. They're unrelated, they're uncorrelated. To be more precise, they're independent. So when two things are independent, the conditional probability is the same as the original probability because of this cancellation, and we just get the probability of A. So that's conditional probability, and look for it on your homework.